Hello students, I welcome you all to this channel on ME Solutions. So today we are going to solve a problem from thermodynamics that has come in the GATE 2020 examinations. So let's read out this problem first. 1 kg of air in a closed system undergoes an irreversible process from an initial state of P1 equals 1 bar and T1 equals 27 degrees Celsius to a final state of P2 equals 3 bar and T2 equal to 127 degrees Celsius. If the gas constant of the air is 287 joule per kg Kelvin and the ratio of specific heats is gamma equal to 1.4, what is the specific entropy of the air in the process? So we have been given four options. So let's try to calculate the entropy change of the system. Entropy change of an ideal gas. So as we know that H equals U plus PV, where H is enthalpy, U is the internal energy, P is pressure, V is the volume. So if we differentiate on the both sides, we'll get dH equals du plus so now we can expand this using the chain rule of differentiation. dH equals du plus P dV plus V dP. So from first law of thermodynamics we can say that dQ is equal to du plus P dV. So we can simply replace du plus P dV in this equation by dQ. So which gives us dH equals dQ plus V dP. Now we can write dQ as TdS, where ds is the change in the entropy. So let's put this value directly into the equation. We'll get dH equals TdS plus VdP. So if we take VdP on the left hand side, we'll get now let's divide both sides by temperature. So we can write dH, that is a change in enthalpy, as specific heat capacity at constant volume multiplied by the change in temperature. So now we can write Cp dt upon T equals VdP upon T, or we can write ds equals Cp dt upon T minus VdP upon T. So for ideal gas we know that PV equal to nRT, or simply PV equal to RT. From here we can get V by T equal to R by P. So now again we will substitute this value into this equation. We'll get ds equals Cp dt by T minus V by T, that is we are replacing it by R by P, into dP. Now let's integrate both sides of the equation. from state 1 to the state 2. So we can get S2 minus S1. There is a change in entropy S. S2 minus S1 will be Cp natural log of T2 by T1 minus R natural log of P2 by P1. So this gives us the net entropy change of an ideal gas which is going from state 1 to state 2. So now let's look at the problem. So in this problem we just have to now put the values in the equation that we have got. So we know T1, T2, we know the value of gas constant, we know gamma. What is unknown is the specific heat capacity. So we know that gamma equals Cp by Cv and Cp minus Cv equals the gas constant. So we can put the value of Cv in this equation. So what will we get? Cp will be gamma minus 1 by gamma. So we'll get Cp as gamma R upon gamma minus 1. So let's put this equation. So put this value in the equation. We'll get S2 minus S1 equals gamma R by gamma minus 1 to natural log of T2 by T1 minus R natural log of P2 by P1. Now if we put the values of the pressure, the temperature and the gas constant, what will we get? Always remember to convert the temperature from degree Celsius to Kelvin. Whenever the temperature is given in degree Celsius, so you should try to convert into Kelvin first. It will be 27 plus 273 T1 will be T2 127 plus 273. It will be 400 Kelvin. R is given to us, that is about 287 joule per kg Kelvin. So here the value of R is given in Kelvin, so that is why we have to change the temperature into Kelvin. The value of gamma is given to us, that is 1.4. So if we put the values, what's the value of R? 287. What is the value of P2? The P2 is 3 bar and P1 is 1 bar. So if we solve this, we'll exactly get the value to be about minus 26.3 joules per kg Kelvin. So the answer is C part. So thank you very much for watching this video. I hope you like this video. Kindly subscribe to my channel, ME Solutions. Goodbye.